Welcome to my YouTube channel. So in the today's video lecture, I am going to start with the digital system design laboratory introduction part. So far I have discussed the different type of laboratories and I have already discussed about the different lectures like in communication engineering and VLSI technology. Today in this lecture, I am going to start this certain laboratory which is known as digital system design laboratory. So this is must be remembered that this laboratory in some other courses may be given the name as digital circuit design lab, or it may be also called as digital electronics laboratory. So generally this subject is actually being taught in second year of electronics and communication engineering, or maybe in some other courses. Here I am discussing about the course which is KEC 352, which is running in the BIT Jhansi in the Department of Electronics and Communication Engineering. So let's begin this discussion about the Digital System Design Lab, its introduction part first. So in this laboratory, you can see that basically these are the different list of experiments that is given in our syllabus, okay, that we have to go through. For example, it is the introduction to digital electronics lab, okay, nomenclature of digital ICs, specifications, study of the data sheet, concept of VCC and ground, verification of the truth tables of logic gates using TTL ICs. Then we are having the implementation of the given Boolean functions, verification of state tables of RS, JK, T flip-flop, D flip-flop, and so on. So there are so many experiments which are actually given in this suggestive list of experiment that we have to perform during this course. So I request all the viewers who are watching this particular video, if their subject is not yet started, then please go through a certain basics of the digital electronics theory part. Okay, once you know theory, then it will be easy to understand how to perform these experiments. So in digital electronics, even if you have not started this subject, I can guess that most of the viewers and the students must be knowing that we are having a different logic gates, because we already studied these things in our 11th and 12th courses. Okay, so you must be aware that what kind of digital logic gates that we have. Okay, and also when you introduced in your means engineering course, must be studied these things, okay, in your basic electronic courses. Okay, so let's begin this one. So in the digital system design laboratory, we need to perform these experiments. Okay, so I will be doing these experiments one by one. First of all, I would like to first give you a little introduction, and then we can start doing our experiment. So you remember that we have to perform this experiment in the laboratory by using the certain kits. Okay, either we can have the breadboard. Okay, onto the breadboard we have to use this logic gates, okay, which will be available in the form of ICs, and then we have to verify its functionality. Then we have to make the digital different digital circuits, okay, based on the digital logic design methodology. Okay, how to design different type of circuits, okay, that we have to look at. So in this lecture, I'm just going to start you means basically I want to give you certain introduction about this laboratory. So these things you must be aware that in the digital electronics, you must be heard of this AND gates, OR gates, inverters, buffers, okay, NAND gate, NOR gate, and exclusive OR gate and exclusive NOR gates. So these are the different logic gates that we have in our digital electronics, and by using these gates we can implement the different digital functions. Okay, we have to implement the digital functions. So here you can see that we have the AND gate whose symbol is given here. Okay, it will be like this. and in which we are having the two inputs X and Y, and based on the logic levels at the inputs X and Y, we are going to get a certain output at the output pin F. So here we can have the algebraic function for AND gate that will be F equals to X dot Y. Okay, so that will be the function of our AND gate. It will be realizing X dot Y. So here is the truth table for this AND gate. You can find that for these combination of inputs, okay, X and Y, we are giving the input as equals to 0, 0, then 0, 1, 1, 0, and 1, 1. You remember that these are the logic bits. Okay, you remember that it is a logic 1. Whenever we are writing 0, it means that it is logic 0. Okay, and whenever we are writing 1, it is logic 1. Okay, so when we talk about the positive logic, remember that this 0 reflects the low voltage levels, okay, and this 1 reflects the high voltage levels. So as we know that in the case of AND gate, it has to be performed this particular function. So this output F will be given by this particular expression. Okay, so whenever both the switches is both the inputs are equals to 0, 0, the output will be remain 0. When it is 0, 1, again the output will remain 0. Okay, means it is voltage level at the output will be 0. Okay, similarly, the voltage level at the output will become 1 when both the input is equals to 1, 1. Similarly, we can have our OR gate in which its function is X plus Y. Okay, so if you see this function X plus Y, we can have this truth table, okay, in which we are having this input combination, and based on this input combination, we can get this particular output. So those who are studying this digital electronics first time, you please go through the books and please see this explanation of the AND gate and the OR gate. You must be aware that the AND gate is also represented as the series switches. Okay, so it is also regarded as like a series switch. So whenever we have a particular input at one point, and if we want to send it to the other point, there will be two switches that will be connected in this series. If both the series switches are closed, then only this input signal can be passed to the output point. Okay, so that closed switch will be regarded as here logic 1. Okay, here it will be regarded as logic 1. Whenever the switch is opened, it will be regarded as logic 0. And therefore, whenever there is only one, even if one switch is open condition, if it is in the open condition, then the signal cannot reach to the output, and therefore our output F becomes 0. So similarly here you can also observe that whenever one of the switches in the open condition, okay, the output remains 0. When both the switches are closed, when it is 1, 1, when it is logic 1, then the output is becoming 1. So these are the truth tables of the AND and OR gates. We are having the inverter in which whatever the signal that we give, when it is given as logic 1, it will be becoming logic 0 at the output, and whenever it is a logic 0, it will become logic 1. So that we can see from this truth table. Okay, similarly we are having the buffer signal, okay, buffer circuit. Then we are having the NAND gate, NOR gate, then exclusive OR gate and exclusive NOR gate. So these are the different graphic symbols of the different gates that we have, and then its corresponding algebraic functions that it performs is also given here, and then we have this truth table. So basically what we need to perform in the case of a digital system design laboratory, first of all, our very first experiment would be to verify this truth table for each and every logic gates. Okay, so though we are having total 8 logic gates, we can verify its truth table by having this AND gates and then applying this inputs, okay, X and Y, various voltage levels to this input pins we can apply, and then we can verify this truth table, okay, whether it is functioning properly or not. So that we have to verify in our laboratory. So once we understood these are the different logic gates that we have and its corresponding algebraic function and its truth table, now we have to look at that basically this logic gates that we are going to have is actually not available in the form of discrete components, but rather it will be available in the form of IC. Okay, IC means it is integrated circuits. So generally, the integrated circuits is classified into this 5 categories. You remember this 5 categories of the integrated circuits. Based on the number of components, you can say, or you can say the number of logic gates that will be available in that particular IC. So based on that, we can see that we are having like SSI means small scale integration. This is medium scale integration, large scale integration, then very large scale integration, then ultra large scale integration. We do have GSI, which is a giant scale integration. Okay, so based on the number of components that will be integrated onto the given IC, that will decide which particular technology that we are using. For example, if SSI, the number of components would be less than 10. Okay, in the case of MSI, this range will be something less than 1,000. Will be your MSI technology. By having the LSI technology, we can integrate more than 1,000 component, and it will be having components as large as equals to 20,000. Okay. Similarly, in the VLSI technology, we can add more and more components, and that components will be something in this particular range that will be 20,000, in between 20,000 to 10 lakhs. So this way, the number of components that we can add onto the single means onto the IC chip. Okay, you remember that we don't have to increase the size of the area of the IC. Okay, but rather within the same area we need to reduce the size of the components so that more and more transistors, you can say, or more components we can integrate within the same area. So that's why these are the different integration techniques that we have. Okay, so these are the different techniques that you have to remember. Why we are studying this? Because we already know that this logic gates will not be available in the form of discrete components. Okay, it is not available in the form of discrete components, but rather it will be available in the form of ICs. Okay, integrated circuits. Okay, so most of the ICs that we are going to see in our digital system design laboratory, you will find that it is either SSI technology based or it is MSI technology based. Some of them are maybe on the LSI based system, LSI technology based ICs. Otherwise, most of them will be either SSI or MSI. So now here you can see that we can categorize our ICs like based on the level of integration, or it may be on the based of digital logic family. Okay, as I said that the level of integration means the number of components or logic gates that we can have onto a single package or IC. Okay, so based on that we can categorize our IC. Similarly, in the digital logic family, you will find that the way we actually fabricate our logic gates. Okay, because each and every logic gates will be fabricated out of a certain electronic component. Okay, so basically it is based on the basic electronic component, you can say, or basic electronic circuit which is used to implement the logic gates. For example, here we can see one example of NOR gate, which is actually consists of the components like resistor and transistors. Okay, so because it is consist of resistors and transistors, this particular NOR gate is comes under the RTL logic family. So what does it mean by RTL logic family? It is composed of resistor and transistor. So that's why this name RTL is nothing but it is a resistor transistor logic. Similarly, here you can see another example of the DTL NAND gate, okay, which is our diode transistor logic, because here we are using the diodes and the transistors. Okay, so that's why its name is given as a diode transistor logic NAND gate. So you remember that this categorization is based on basic electronic circuit that we use for making our logic gates. So based on that, you can find that we are having total 6 categories like RTL, okay, DTL, then we are having TTL, transistor logic, then we are having ACL, emitter coupled logic, and then we are having MOS devices, which is metal oxide semiconductor devices, okay, and CMOS is the complementary MOS devices. We do have a certain properties of all this digital logic family. Okay, remember that we do have a certain properties of this digital logic family. Once you will study this theory part of the digital electronics, you will find that you have to go through a different properties of this type of logic families. So what are those properties are like fan out, what will be the propagation delay, what will be the power consumption of this type of family, okay? So that we need to talk about. So mostly you will find that in most of the cases, these all logic families are having their own merits and demerits. And RTL and DTL circuits are rarely used, okay? It is not used in practical sense, but we are using the TTL, ECL, and the CMOS logic families. So here I'm just going to give you a brief idea about the properties of the TTL logic gates, okay? Means a transistor logic gates. So as name suggests that if you talk about any TTL logic gates, it means that whatever be the component, whatever be the logic gates that we are going to fabricate, that will be made out of only transistor. Okay, the transistors are the basic components that will be used for fabricating the logic gates. Fine. So you can see that in the TTL series, we are having the different categories. Here you can find out the different categories, and these are the different characteristics of this TTL series. Okay, so fan out, you must not be able to understood if you are new in digital electronics. Okay, so right now I'm not going to discuss in detail about these points because it is not required, but just you try to understand that it is having a certain characteristics which is known as fan out, power dissipation. Okay, that will be in the milliwatt. It is written in the milliwatt, and here it is propagation delay in the nanoseconds, and here it is a speed power product, which is measured in the picojoules. Okay, so here you can see that in the TTL only we are having different category, like a standard TTL. We are having a standard TTL that will be identified by the certain series which is written over the ICs. Okay, so if it is just a 7-4, you can think of it as a standard TTL logic gates. If it is a low power TTL, then there will be a prefix of 74L, okay, 74L. So similarly for high speed, it is 74H. But then if it is a short key TTL, okay, it will be written as 74S. So by seeing this different prefixes, okay, you can identify that which class it belongs to. Okay, so that we can easily identify by just seeing these prefixes. And these are the different properties of this particular classes. Okay, you can see these different properties. So here you have to remember one very important fact about the voltage levels that we use in the TTL ICs. Okay, so you remember that because we have to use the TTL ICs only for doing our experiments. Okay, so that's why this voltage level is very important. So in the case of TTL IC, you will find that if you want to give any logic 0 as the input, okay, low level voltage, you can say. So if you want to give the low level, okay, or the logic 0 as the input, then any voltage up to 0.2 volt, or it may be 0 volt, it may be some negative voltages. Okay, so up to 0.2 volt, it can be treated as a logic 0. Similarly, if you want to give the logic 1, at that time, this voltage should be 2.4 to 5 volts. It should be in between this range. Okay, so any voltage in between 2.4 volt to 5 volt at the input pin of your TTL logic gates will be treated as logic 1. Okay, and anything up to 0.2 volt, okay, less than 0.2 volt will be considered as logic 0. So the best practice is to give 0 volt as the logic 0, and to give like voltage 5 volts as a logic 1, so that we can give for giving the logic 0 and logic 1 in our TTL logic gates. So these are some important facts. Now, one more point that I want to make out here is that you can see that this is our one of the transistor, one of the ICs. Okay, so here it is 74LS00. So here you can see that this is 74LS means it is a TTL logic gate, which is LS means LS stands for low power Schottky. Okay, here you can see that we are having this LS series. Okay. So this LS series reflects that it is a low power Schottky. This 74 denotes it is a TTL logic gates. Okay. So it is a low power Schottky TTL. Here you can see that it is a low power Schottky TTL. Now we are having this another 2 digits followed by this LS, okay, which is 00. So here this 00 meaning is that it is a NAND gate. Okay. So I will give you all these numbers. Okay. So how to identify this 00 actually reflects that it is a NAND gate. Okay. So one very important thing is that you can see that basically in this particular NAND gate IC, you will find that there are certain number of pins which are available at the outside of this particular IC. Okay, so here you can count that how many pins we have. Okay, it is 1, 2, 3, 4, 5, 6, 7, and another 7 pin is at this side. Okay, so in total this 74 LS series, okay, or any TTL logic gate that we are going to use in our laboratory will have the 14 pin IC. Okay, it is a 14 pin IC. You remember that there will be total 14 pins. Okay. So how to identify these pins? Because once you will see these pins, okay, we need to follow a certain convention to identify these pin numbers. Okay, because we are having total 14 pins in this particular IC. Okay, then how to identify this pins is very important. So that we need to understand. For example, here you can see that in this particular IC, onto the top, you will find that we have a C groove which is cut at the top of this particular surface. Okay, and then here you can see once we have this groove onto the surface, you will find that here we have the first pin and then we have the second pin. Okay, so we need to start giving the number from this side. Okay, that you have to remember. We have to start counting our pin from this side. So this will be our 1, this will be second, this will be third, 4, this is 5, this is 6, 7, then this pin will become 8th number. Okay, so this is 8, 9, 10, 11, 12, 13, and 14. So this way we are having a different number of pins. Okay, 1 to 7 here, and again we are having the pins from 8 to 14. See, so the same thing you can see here. This is our pin diagram in which you can find that how the components are actually internally oriented. Okay, how it is made a connection internally. So here you can see that we are having the pin like this is the pin number 1, this is pin number 2, which are nothing but the input pins to this particular NAND gate. Okay, and then this pin number 3 is served as an output, okay, of this particular NAND gate. Okay, so here first of all, what is the important point that we need to remember is how to identify the pin numbers. So always you have to count this pin number from this C group. Okay, once you will identify this C group, okay, then from here only you have to start counting your pin numbers. Okay, and then you have to go like anti-clockwise, and then you will find all the pin numbers. Okay, identify the pin numbers, and then you need to know this internal pin diagram. Okay, so if you know this internal pin diagram, then only you will be able to tell which one will be the input pins and which one will be used for the output. Okay, so here you can see that pin number 1 and 2 are the inputs and the pin number 3 is the output pin. Okay, similarly 4 and 5 is another input pin, because you can see that in this particular case we are having total 4 NAND gates. Okay, here you can see that we are having total 4 NAND gates. Fine. So here it is, the inputs are 4 and 5, and then again the output pin is our 6th number. Similarly, here you can see that we are having the pin number 7, which is actually served as a ground. Okay, you have to connect the ground of your circuit to this particular pin. Okay, similarly here you can see that 10 and 9 number pin is actually used for giving the input. This 8th number pin is served as the output. So please do not connect any input to this particular output pin. You have to always take out the output from this pin number 8. Similarly, we have another input pin as pin number 12 and 13, and then we have to take out the output from the pin number 11. Then we have to give the power supply to this pin number 14. So you remember whenever you means making a connection, or if you want to make any logic circuits using this ICs, you have to remember that you have to give a power supply to this 14 number pin. Okay, that power supply that will be required is plus 5 volt, and here we have to give the like ground. Okay, we have to connect the ground at the pin number 7, and this way we have to give the inputs to the certain pins, and then we have to take the output from the other pins. So these are the some important points. So basically we have to first know the transistors means IC numbers. Okay, which particular IC we have to use. Okay, and how to identify the pin numbers. And once we identify the pin numbers, we should must be aware about the pin diagram of this particular IC, which is the internal pin diagrams. Okay, after knowing these things, you remember while performing any experiment, you have to mount this IC onto the breadboard. Okay, onto the breadboard. So this is our breadboard. So those who are watching this video first time, and those who are not having any idea about the breadboard, I have already made a detailed video lecture onto the same topic. How to means what are the characteristics of the breadboard? Okay, how to make the connections? Okay, how to mount the ICs onto the breadboard. Everything I have explained in that particular EDC lab introduction lecture. Okay, so I have shared the same video link into my description box. So those who are new, they can go through that particular lecture to having a proper understanding of this particular breadboard. So just for your sake of completeness, you remember that in the breadboard, we will be having certain horizontal connections at the top, and here it will be a vertical connections. Okay, and again in this section we are having the vertical connections, and again at the bottom side we are having the horizontal connections. Okay, the meaning is that all these holes that you are able to see are actually internally connected horizontally. Okay, and here the holes which are connected in this particular segment, they are actually connected vertically. Okay, similarly here again it is connected vertically. Okay, you remember that it is shorted vertically. Okay, so to connect an IC to this particular breadboard, we have to connect this side, one side pin to this particular top section, and the another side pin should be connected to the bottom section. Okay, you remember this. Okay, you cannot mount this IC like onto the one side. Okay, you cannot means connect this particular IC to the top section or only in the bottom section. Okay, so one side pin should be connected to this side, and another side pin should be connected to this side. So only this is the way of connecting the IC. Okay, so this way we have to make the connections, and then we have to complete our circuitry by giving the power supply and connecting the like our grounds. And then to identify the circuit operation, we need to also connect the LEDs. Okay, so that whenever LED glows, we will be able to understand that it is a logic high as an output, and whenever the LEDs is switched off, then we can understand it is output is at logic level 0. So this way we can identify the operation of any logic gates. Fine. So now one more important point is, as I said, that we are having a different logic gates. Okay, so we have to just see what are the different logic gates that we have, and what will be its identification. Okay, how to identify by just seeing the this series numbers. Okay, so here you can see that what will be the IC series that we have to see. So it is 7400. Okay, whenever it is not written like 74LS00, so you remember that it is a standard TTL. Okay, so it is 7400. So there here it is 00 means it is a NAND gate. Okay, it is a 2-input NAND gate, and total 4 number of NAND gates are available within the same IC. So it is also called as like quad 2-input NAND gate. Okay, you remember that generally it is referred as quad. I have already written here. Okay, you can see it is a quad 2-input TTL NAND gate. Okay, so it is a quad 2-input NAND TTL NAND gate. Fine. Similarly, here you can see that we are having the quad 2-input NOR gate. Okay, so we are having like input pins, and then we are having the outputs. Okay, similarly, this number you can remember. Okay, it is 7402. Okay, if it is a 7402 IC number, then it will be corresponds to your NOR gate. Similarly, for hex inverter, we are having this 7404. Okay, then 7408 is for AND gate. Okay, then 7410 is again a NAND gate. You see that it is a 3-input NAND gate. Okay, here we have 7400 as a NAND gate, but it is a 2-input NAND gate. And here we have 7410, which is a 3-input NAND gate. Okay, so how many NAND gates we can accommodate within this IC? Only 3 NAND gates we can accommodate. Similarly, we have the 7420, which is a 4-input NAND gate. Okay, it is a 4-input NAND gate. So here you can see that we are having the 4-input NAND gate, and then we have like 2 NAND gates we can accommodate. For 2-input OR gate, this IC number is 7432. Okay, similarly 7486 is for your 2-input XOR gate. So these are the different series, IC series that we have to remember. Okay, you have to keep in mind. Okay, while doing the like your experiment on digital system designs. Okay, so I hope you must be able to understand this introductory lecture. Okay, you please go through this lecture well, and then try to understand this internal diagrams. You have to remember it. Okay, because whenever you make any logic gates or logic circuits, okay, that time you have to remember that what will be the pin diagram. So once you understood the pin diagram, then only you will be able to make any circuitry. So I hope this lecture must be you must be able to follow. If you have any further doubt, let me know with your comments. So in the coming video lecture, I am going to start with our first experiment, that is identifying the truth table of different logic gates. Okay, you remember that the experiment has to be performed in the laboratory by having the breadboard ICs. Okay, then making a connections. Okay, but here onto this online platform, I will be doing the same experiment by using the MultiSim software. So I have already explained about the MultiSim software in my previous video lectures. So those who are new, please go through that lecture to understand the basics of the MultiSim. So I hope you must be clear with this lecture. If you have any doubt, let me know with your comments. I will be discussing our experiment in the next video lecture. So thank you for watching this video.